For decades, generating digital video meant building complex 3D meshes and polygons. Modern AI generation operates on a different foundation, built using a random number generator and the laws of physics. Open-source models like WAN 2.1 begin every generation with a block of pure random pixel noise. At the start, there is no recognizable image, just a chaotic field of static. This is where the transformer architecture comes in. It scans the noise for faint probabilistic patterns, much like seeing shapes in clouds. Over a cycle of 50 steps, the transformer identifies these structures and feeds the refined data back into itself. Through this recursive loop, the model generates complex new structures directly from the randomness of the initial pixel seed. Converting a user's request into video requires solving a mathematical mismatch. A string of text and a grid of pixels exist in entirely different dimensions, making it impossible to combine them directly. A model called CLIP bridges this gap by mapping the text prompt and image into a single 512-dimensional coordinate. Through contrastive learning, text and images sharing a meaning align perfectly in this space, while unrelated concepts are pushed to opposite sides. This creates a latent space, a universal geometry where concepts, words, and pictures all occupy the same mathematical locations. To teach a model how to build an image, we first teach it how to destroy one. This involves taking a clean image and iteratively adding noise until all structure is gone. This diagram represents data as a sharp spiral. This destruction mimics Brownian motion, a random walk. The model predicts this noise, creating vectors pointing back. But perfectly following these arrows makes trajectories converge at the graph's mathematical center, missing the sharp edge. This center point is the statistical average, a blurry, featureless smudge. To maintain detail, we add random noise back after every step. These stochastic jumps force the particle to zigzag wildly until it lands on the sharp, high-resolution boundary. This injection of chaos is what prevents the generation from collapsing into a blurry average, allowing it to snap into a realistic, sharp image. The final requirement is steering this reverse diffusion process toward the specific subject the user has requested. The CLIP text vector acts as a gravitational pull, tilting the field so zigzagging particles are drawn toward a specific data category. Negative prompts function similarly by repelling the trajectory, pushing the generation away from unwanted regions, like anatomically incorrect data. The text prompt serves to reshape the physics of the generation space, ensuring the particles settle into the exact outcome requested. We can now track the entire process chronologically. It starts with a text prompt becoming a vector, which sets the gravitational target for the generation. A random number generator provides the initial noise, and the model runs Brownian motion in reverse to pull structure out of that static over 50 iterations. This framework relies on 3 distinct layers. CLIP provides the geometry of language, diffusion manages the physics of noise, and the transformer handles the iterative math required to reverse the destruction. The result of this synthesis is a lifelike video, created by applying physical laws to the mathematical